Okay, so here is the second part of the video on magnets. So we'll spend some more time with this PhET simulation, but I just wanted to show you this in terms of, because this drawing is better than what I'm going to draw. So here you've got a bar magnet, and you have a north pole and you have a south pole. And what's important is that notice that the direction of the field. So the direction of the field is what I call the Confederate designation. It goes from the north to the south, no matter which side that you're on. So that's what I was trying to show you when I put those iron filings over the top of it, is that you have a north pole coming around like this, and it's in a defined region of these fields. So this is what the iron filings were lining up with, was it was lining up with these magnetic fields. So now what we'll see is that if we take this and we move it inside a coil, you'll notice that it generates electricity. So we're going to spend a lot of time talking about that, but that's one of the key things that allows us to have electricity in terms of producing it from like a generator, is that basically you move a magnet in and out of a coil, and that generates a voltage. So notice you get a negative voltage in one direction, you get a positive voltage in the other one. That's how, oddly enough, how you generate AC current. Wait for it. There you go. There's your spoiler alert. So here's, for now, all I want you to get out of this is that the magnetic field lines are starting from the north and they end up in the south. That's why I call it the Confederate designation. Okay, so that's what I said. My drawing is much more crude. It isn't near that cool, but you get the idea. So here's this Confederate designation. You're going to go from the north to the south in terms of how you're going to draw the magnetic field lines, okay? So I cannot emphasize this enough. Oh, I didn't mean to do that. Is that this is one of the key things that you've got to be able to figure out when you're talking about a magnet in terms of the direction of the field lines. They're going to start in the north and they're going to go around into the south. Now, in terms of direction, north, south, that type of thing. So this is where this gets a little bit wonky. So we define a direction in terms of the north and south by the direction that the north pole is going to point. Okay, so this is where this gets a little bit weird. So if you look at this strange rock that we're on, we have a liquid iron core that's generating a magnetic field. So when you define north, okay, and this is the whole key in terms of the direction of the north pole, if you have an external magnet and it's going to point in this direction, that's actually pointing towards the south pole. So what we call the north pole of the Earth is actually the south pole of a magnet that's inside of it, okay? Which is a little bit like, oh, seriously, yeah, because that's how you define north, okay? So if I were to put a magnet out here, okay, and this end would be like the north end. So that north end of this magnet is going to point towards that south pole. If I try and bring that north end of the magnet here, it's going to repel, and it's going to go in that opposite direction, okay? So that's what I want you to get out of this. Okay, now don't flip out and go, oh, we've been lied to. No, you haven't been lied to. It's just how we define magnetic fields. Don't worry about it. Now, when we talked about, I did that demo with the string and we pretended that it was a wire. So one of the things that you've got to be able to do is this right-hand rule. Now, imagine that this is my right hand and here's my thumb, okay, and the current is going in this direction. So I point my thumb upwards and then I curl my fingers around in this direction. Hey, that's not all bad. So one of the things that you've got to be able to do is, how do we define something going into the field or into the page or out of the page? So what we do is we use X's and we use dots, okay? So here's the designation. X's indicate that the magnetic field is going into the page, okay? Dots or circles indicate that it is coming out of the page. So here's how I always remember this. if you're a pirate and you're looking for buried treasure, X is going to mark the spot. That's where you're going to dig. So if the current is going in this direction and I wanted to indicate the magnetic field that's on either side of this wire, what I would do is that, so here's my wire. So the magnetic field is coming out of this side. God, I wish you could like film this at the same time. But imagine that here's my fingers and they're pointing out of the page. So I would put dots on this side because they're coming out of the page like this. Then, but on the other side of the wire, they would be going into the page and I would put X's. So I put my thumb in this direction, I curl my right hand, then I got dots on this side, I got X's on this side. Now, the opposite is true if I send the current downward. So if I send the current down, and this is in the plane of the page, so I'd point my thumb downward like this, okay? So I'd point my thumb down. Then this would be like the back side of my hand. Visualize that's the back side of my hand. So then I would have X's on this side, and then I would have O's on that side. So it would be going into the page here, and it would be coming out of the page on this side. Now, like I said, we're going to have variations on this theme, but that's kind of the beginnings of this idea. Okay, now, in terms of how you calculate the strength of magnetic fields, okay? If you have the magnet in a ring, and let's say that the current is going in this direction, okay? So you've got a circular magnet or a circular wire and like a coil, and the current is going in this direction. So you point your thumb in this direction, and then, so if you point your thumb in that direction, then on the top, you would have X's, and then inside of there, you would have O's, because your fingers would be pointing into the page here, and they would be coming out of the page on the inside, okay? Now, if you reverse it and had the current going in the opposite direction, then you'd have X's on the inside and O's on the outside. So if you calculate the magnetic field, so when you see this letter B, B stands for magnetic field, magnetic. If I could spell, that would help. Magnetic field strength, and that's mu naught I over 2R, okay? So if you look at this mu naught, and so mu naught is your, if you remember, vacuum permeability, and that is 4 pi times 10 to the minus 7th, and it has Tesla meters over area. So the magnetic field strength is going to be measured in Teslas. So if you look at what happens with the units, so mu naught has units of, we'll change the colors a little bit, Tesla meters over amps, okay? And I screwed that up. That's not area, that's amps. That's amps. So what's going to happen is that the meters are going to cancel out. This is current, so that's going to cancel out those amps, and you're left with Teslas. So that's what that magnetic field strength is going to be measured in. So now, if you have a, hold on. Now, if you have a wire, there it is, lost track of what I was writing, and you want to find the magnetic field around the wire, so if we reverse this and say, oh, we've got X's on this side and O's on that side, the only way that can happen is if the current is going up the wire, because then you're coming out of the field over here, and then you wrap your hand, and then the fingers would be pointing into the page over here. Now, if it's a wire, your magnetic field strength is, hold on, my pen is not cooperating, is mu naught I over 2 pi r. Now, the reason that we introduce 2 pi r, which is just basically the circumference, so the difference here is that if it's a loop, you use mu naught I over 2r. If it's a wire and you're finding the magnetic field strength around it, you use mu naught I over 2 pi r. So this is basically giving you the circumference. Now, here's the deal. This is the beauty of this. Notice as the radius gets bigger and bigger and bigger, you get a bigger and bigger and bigger circumference, and that magnetic field strength becomes smaller and smaller and smaller. So this is like a classic situation of an inverse relationship. Also notice that as your current becomes stronger, your magnetic field strength becomes stronger because you have more of a current going through there, creating more and more and more of a magnetic field around it. So it's inversely proportional to the radius, directly proportional to the current that goes through it. So this first assignment is pretty short. I'm just going to scan that image of that assignment and I'm going to give that to you. So this is just kind of an introduction so you can kind of get a feel for magnetic fields. If you want, I would suggest that you read chapter 24 because of the fact that that has a lot of good stuff in it. So, all right, kids, I'm done. So this is going to be the second